So we are dealing with iron oxide nanoparticles because of their low cost, low toxicity, and super paramagnetic nature. They are the highest magnetically responsive oxide nanoparticles, and we're using polyurethane linkages because of their porous properties and hydrophobic nature. So current filtration methods require different filters for each pore size needed, and due to the fact that iron oxide can incorporate itself into polyurethane linkages, we can make a magnetically alterable foam.
Our objective for this project is to create a reusable magnetite incorporated polyurethane sponge in which you can control the pore size magnetically for the purpose of multiple filtration. Current filtration devices demand different filters in order to separate the different substances. If a magnetically modulated membrane that is capable of filtering several substances could be created, it would be convenient in society in various ways, such as saving money, time, and making life easier, which is my motivation for this project. These are the different chemicals that we use in order to create our sponges. We use polyurethane hydroxyl terminated, and that's the backbone of the sponges. And we incorporate a saturated nanoparticle solution into our sponges. Next, we incorporate tannic acid, which is our cross-linker, and we add stannous octanoate, and we add 1 milliliter of hexane diisocyanate into our sponges. And sponges 36 and 39 were all created with roughly 4,400 milligrams of polybutadiene, 1 milliliter of concentrated nanoparticle solution, 50 milligrams of tannic acid, various amounts of stannous octanoate, and 1 milliliter of hexane diisocyanate. Sponges 32, 35 were made with the same. They were made with the same chemicals, but what we changed was our catalyst, and we changed that from stannous octanoate to bis dimethyl amino ethyl ether, and you'll see how that changes our sponges. When I used the stannous octanoate while creating the sponges, it gave the sponges more rigidity than when I used my new catalyst. The sponges had a slight difference in physical and mechanical properties. The more I increased the catalyst, the more porous the sponges were. On the other hand, with the new catalyst, as you can see, it drastically changes the physical and mechanical properties so much that they did not even look like sponges. The turnout of these sponges were rock-like, but they were very porous and fairly magnetic. But one obstacle that we are not able to overcome is that at this point, finding a uniform pore size for our foams, we cannot control how the carbon dioxide bubbles form while the foam is in the developing process. The pore sizes vary within each sponge. If the pore sizes are not identical, then the foam will not be capable of effective filtration. If you take a look at the images A through D, you can see the different sizes of the pores in our sponges. Image C looks more uniform, more like a sponge. I believe the pores are more uniform in this sponge because we had lower amounts of catalyst than the other sponges, which allow the sponges to contain more material than pores. This graph underneath of the pictures is my compression modulus in the form of a stress and strain curve. I characterize the sponges on a magnetic deflection stand using 5 different beakers. Each beaker had a different mass. I placed each beaker on my sponges and watched how much the sponge deflected. The lower the sponge deflected, the higher the compression was. And these are the sponges that these are the 3 sponges that I tested 38, 39, and 37, and these are the comparisons of these sponges. What I concluded from this test is no matter how much of the new catalyst I used, it just did not work. It produced a rock-like substance, and it changed the physical and chemical and mechanical characteristics of my sponges. So what we're going to do in the future is go back and use the stannous octanoate in our future sponges to produce a better rigidity and better compression results. Also, what I plan to do is figure out what could be done in order to increase magnetism in these sponges. Likewise, I can discover how many substances could be filtered, what kind of substances, and if this would have a warranty.
Thank you. Before our next presenter, we did have one question that came in for Sierra. Actually, a second question is coming in from Stephen. The first question is, what would happen if the tannic acid concentration was varied?
If the tannic acid concentration was varied, well, the tannic acid is what we use for our urethane linkages, I believe. So the more linkages we have, the more material that we have in the sponges, and the more material that we have, the less pores that we have in sponges.
Okay, and the second question was, what is the main difference chemically between the 2 catalysts?
I'm not too sure of the main difference between the 2 catalysts, but all I know is that it changes our sponges. I'm not too sure of the difference in the catalyst. I just know how it changes the sponges.
Okay, thank you. And if you have any questions, we're going to proceed to our next presenter. If you have any questions, just please type those into the chat window. I'll save them for the end. And we're going to switch over to the next presentation, and I'll turn it over to Lynn.
So to begin, I had to make our iron oxide nanoparticles, and we did this by using the co-precipitation method, which means that I reduced an iron salt mixture that contained ferrous chloride, ferric chloride, and sodium hydroxide in order to form the iron oxide. Then once I had this mixture, I separated it into separate 45 milliliter centrifuge tubes. I centrifuged it, poured off the supernatant, added water, and repeated the process until a pH of 7 was achieved. And another way to have your iron oxide nanoparticles is actually purchase iron oxide powder. So in order to make the foam, I first started with image C, which is our polybutadiene hydroxyl terminated. It acts as a diol and a polyurethane backbone for our sponges. And I incorporated image A, which is our magnetite or iron oxide nanoparticle. Then I added the tannic acid, which is image B, which is a polyol and a crosslinker for our sponge. And I added our catalyst, which is image E, our stannous octanoate. And finally, I added image D, which was our diisocyanate that began our reaction in our sponge. It reacts with the hydroxyl groups in the tannic acid, image B, and the polybutadiene, image C, and creates polyurethane linkages. And then it also reacts with our aqueous iron oxide nanoparticle solution in image A to form carbon dioxide bubbles, which in turn create the pores in our sponge. So I did a DLS reading of our iron oxide nanoparticles, and I got that they were mainly around 60 nanometers in size. And this is a TEM image at 200,000 magnification of the nanoparticles, and as you can see, they're polydispersed. So this is a stress strain curve of the 3 sponges that I tested, and the slope of this curve shows the compression modulus of our sponges, which corresponds to the rigidity in each sponge, which I'll discuss in the next slide. And initially, we found that sponge B appeared to be more magnetic, so we did a TGA analysis of it to find the percent composition of the iron oxide nanoparticles, and we found that it was roughly 6% nanoparticles in the sponge. So as you can see, the compression modulus decreases from sponge A to sponge C, and sponge A was the most rigid of our sponges, whereas sponge C was the most flexible but also durable sponge. And it also, I guess it was caused because of the increase in the polyurethane backbone and the catalyst. So what we concluded is that the idea of a magnetically alterable filtration system would be nice, but we're not sure if the materials that we're using here would be practical. So the reasoning is that in order to have a filtration system, or a magnetically alterable one, you would want the sponge to actually shrink in size when a magnetic field is applied, and we haven't seen that in our studies yet. And also, we see that changing the substances, or changing the polyurethane and the catalyst affects the mechanical properties of our sponge, but we're going to have to do a little bit more work into that to further investigate the effects. So in our future work, we hope to do studies on the maximum loading of iron oxide nanoparticles in our sponges, and that would be around 67% of concentration of the nanoparticles. And we also hope to use cobalt nanoparticles because they are about 3 times as magnetically responsive as iron oxide, and gold-coated magnetite, which would allow us to use the optical properties of gold so that you could actually see the pore size shrinking. And then once you would have an ideal sponge, then replace those gold-coated magnetite with silver-coated magnetite so that you could have antibacterial qualities in your sponge.
Thank you very much. And we have a couple more questions that have come in. So first of all, the next question that came in is, what sizes of pores do you expect for the case of an ideal sponge exhibiting a high efficiency?
At the moment, I'm not sure. We've been looking at our SEM images and trying to figure it out, but I don't have an exact number. So maybe I would have to contact you later and let you know.
Yeah.
Same thing. We have no minimum pore size or maximum pore size that we came up with to have for the sponges, but we do use SEM to vary the pore sizes and see the differences in the pore sizes in our sponges, but we do not have a exact pore size that we want to have for our sponges.
Okay, we have another one, and another question and some comments coming in. The next question from Stephen: if polyurethane sponges are not ideal, what other way could you suggest to create a magnetically modulated sponge?
Well, people have done work on using gels, and from what I could tell, they had a very magnetically alterable substance, but they had to create their pores by using, I guess, little metal rods. So the pore size didn't actually get down into nano size. So I would say that you would want to try and have a substance that would be able to create pores that were small enough to actually filter bacteria and whatever else you would want, maybe even urine and everything like that. But I don't know if that would work or not.
Okay, and I actually had a question. I mean, the concept of magnetically altering a sponge is kind of fascinating. I know that the research seems to be very early, but is there a driving application, industrial or some dream high in the sky that is funding all of this work, and or it's just very interested in you guys and other researchers come up with a successful version?
Well, I know that we are no longer funded by NASA, but I believe this project was started by NASA because of all the filtration systems they have to have when they go up to space. They have to have a different one for air, for water, for their urine. And so if you could compact that all into one system, you would greatly decrease the cost of actually sending it up, because you would decrease your weight by however much you end up decreasing.
Yeah, I just saw the end of the space shuttle program yesterday. The space shuttle cost something on the order of $100,000 a pound to send things up. It's very interesting. And we had another question come in. Are the nanoparticles cross-linked into the sponge? Do the nanoparticles disperse, or do they agglomerate before the sponge is formed?
Well, we plan to do some testing to see if the nanoparticles disperse through the sponges. I believe the nanoparticles stay at the bottom of the sponge more than so at the top of the sponge, but we try to mix up the sponge in the process of making the sponge, but I don't believe that they disperse evenly throughout the sponge.
We've kind of come up with a better method of actually making our sponges, because at first we didn't think about the fact that your sponges or your polybutadiene and your nanoparticles would have to be fully mixed, I guess, before you actually add anything else. So what we've been doing is actually using a magnet to move the magnetite throughout the polybutadiene, and so it kind of engulfs in it, and that way we have better uniformity throughout.
Okay, that's interesting. It sounds like you might need to make your sponges in outer space, so you don't have some gravity pulling these things down. If we could just take your entire lab up there, that might be a few $1,000s too much. So that was the end of today. We had a shout out from Panda and Scott. Said good job on your magically magnetic sponge.